Good. Yeah, thank you very much. And first of all, I would like to use the opportunity to thank the organizers for giving me the opportunity to talk here a little bit more about my work on exploring the coupling of Mott insulators to elastic degrees of freedom by pressure tuning. And by pressure, I mean both hydrostatic and uniaxial pressure. And so before I get started, I would like to acknowledge all the people that are contributing to this work. So the most recent work that I'm going to show is actually a result of now my time at the Max Planck Institute for Chemical Physics of Solids in the Department of Annie Mackenzie. But then also I'm going to show some results that I did in collaboration with the groups of Paul Canfield and Yuji Furukawa at Ames Lab, and obviously also from my time in Frankfurt in Michael Lang's group. And I would like to also acknowledge the theory support of Markus Gast, and samples were provided by Tai Kong from back then Bob Carver's group, but now at the University of Arizona, as well as Bella Lake. And funding for the work over the years has sort of been provided by the DFG throughout various CLCs, but also the 11431 on frustrated magnetism, the Gordon and Betty Moore Foundation, as well as the US Department of Energy. So I guess why we should be interested in lattice effects around the Mott transition was nicely motivated by Jörg already this morning. But as an experimentalist, I want to take a step back and actually first discuss how we can find or how we can verify that the coupling to elastic degrees of freedom is of importance at the Mott metal insulator transition. And so what we need as experimentalists is model systems. And I guess within this audience, I don't have to emphasize too much that these organic materials are really model systems to explore the physics of the Mott metal insulator transition. And this is mostly because they're very highly tunable, as exemplified here by the fact that already very small pressures allow to cross this first order metal insulator transition, which then ends up in a critical endpoint located at around 37 Kelvin, so at a very convenient temperature and pressure range. Now, the idea sort of that pressure is tuning the Mott transition is comes from the fact that pressure is believed to tune the bandwidth, and the Coulomb interaction over the bandwidth is considered as the control parameter of the Mott transition. Therefore, if we change pressure, we can effectively tune through the Mott transition. Now, obviously, if we use pressure as a tuning parameter, this brings up the question of what is actually the role of lattice degrees of freedom at the Mott transition, because pressure in the first instance will modify the crystal lattice and only thereby affect the electrons. But then the electrons can also have an effect on the crystal lattice, because the crystal lattice, in fact, is not completely rigid. It is compressible and therefore can respond to the electronic, to the changes in the electronic degrees of freedom, as pointed out by Jörg this morning. So again, also Jörg already nicely discussed the implications of that to some extent. So from theory point of view, what we expect theoretically comes from basically this bilinear coupling of the Mott order parameter to lattice strain. But what we then are interested in, or what we are measuring in order to see those effects, is something that we call strain-stress relationships. So basically the change of the length of the crystal lattice. So basically a parameter that directly measures the crystal lattice as a function of pressure as we tune across the Mott transition. So if we are at very high temperatures, very far away from this endpoint, we can consider the electrons and the lattice sort of decoupled. So then if we just take a look on the lattice properties, what we expect is a more or less linear change of the length as a function of pressure, which is something which is known as Hooke's law of elasticity, and most of materials show that. Now, as we get closer and closer to this endpoint, we expect that the coupling becomes more and more important. And what the consequence of that is that we expect a very strongly non-linear change of the length as a function of pressure. And this then would be, or this is what is then known as the breakdown of Hooke's law. And so I guess back then in 2016, using a very dedicated setup that allows to measure thermal expansion as a function of hydrostatic pressure in Michael Lang's group, we did those experiments here on kappa chlorine, a material which now has been mentioned multiple times, and indeed found, so the critical endpoint, as I said, is located here at 37 Kelvin, and we found these very strongly non-linear strain-stress relationships up to at least a temperature of 43 Kelvin, so quite high. And if we convert that into sort of a range of temperatures, then we can say that we found a breakdown of Hooke's law in a range of around 20% around the critical endpoint. So, and as also pointed out by Jörg, this is actually not really a small point. It's a wide range around this endpoint, which is then the properties there are determined by the coupling of elastic and lattice degrees of freedom. And this is something which then has been termed as critical elasticity. Now, why are the organics so, there was a fly. So why are the organics so important to actually, or why are the organics so great to find this? Well, we know that the organics have a very large electron lattice coupling. I mean, you can infer that already from the fact that they are very pressure sensitive. So the fact that electron lattice coupling is large in those systems make these systems actually model systems to find effects related to electron lattice coupling. On a, let's say, more wider perspective, the implications of the work that we had done back then on the organics is that in principle, we should not treat the physics of strong electron correlations fully decoupled from lattice degrees of freedom. Eventually, all materials will probably be governed by this or the properties of all materials will be governed by that coupling. And the second important message was that, is that pressure tuning is very important if we want to find, or if we want to discover, tune, and also probe the effects related to electron lattice coupling. Now, again, as Jörg already nicely introduced this morning, pressure is actually a very versatile tuning parameter, and this comes from the fact that it's a tensorial quantity. So basically, we have very different or many different ways of how we can control pressure. And for example, if we choose certain types of pressure, we can control the volume or the symmetry or both of that. And this obviously will be of relevance if we look onto Mott insulators, where, for example, we, in a first naive thought, think that we can control the correlation strength via the volume and something like the frustration via controlling symmetries. And in fact, so it is over the last probably like 5 to 10 years, there has been really tremendous progress in possibilities how to probe strongly correlated electron systems under varying stress conditions. And the stress conditions, for example, include hydrostatic pressure, uniaxial pressure, but also, or even the combination thereof sometimes. And what I also want to emphasize here is that pressure is not only a parameter that can be used to tune a correlated electron systems, but also to probe their properties. And I will show examples of that in just a second. Okay, so the main part of my talk actually will be, in 2 parts, both related to inorganic materials, but related to pressure tuning of materials close to Mott transitions. So in the first part, I want to discuss an example case of van der Waals ferromagnet vanadium triiodide, where we used hydrostatic pressure and specific heat under hydrostatic pressure to map the phase diagram and figure out how magnetism is related to symmetry breaking structural distortions. And then in the second part of my talk, I want to discuss a little bit the aspect of that we can also use pressure to probe properties. And so what I will show is data of the elastocaloric effect of a frustrated magnet under strain. Okay, so coming to the first part, let me give you a quick introduction into the material. So what the type of materials that we are dealing with are transition metal trihalides on honeycomb lattices, which in principle are of interest on the one side from fundamental point of view, because they exhibit often low dimensional and sometimes even frustrated magnetism, and are also of interest from application point of view because they are easily exfoliable. So this is then of interest for people working in the spintronics field. And one example for, at least for the latter is, or the latter motivates some interest in studying ferromagnets. And one example here is the material chromium triiodide, where it was actually possible to exfoliate the material and establish ferromagnetism, at least here in the monolayer limit. So now the material that I will be discussing is also ferromagnetic. It's the material vanadium triiodide. This material was shown to be a Mott insulator with a gap of around 0.6 electron volts. It has ferromagnetic interactions. In contrast to the chromium system that I just mentioned, it has a slightly different electronic configuration. So it's 3D2, meaning it's a spin-1 system with active orbital degree of freedom. In addition, spin-orbit coupling is relevant. And all of these factors here play together in order to establish basically a strongly anisotropic ferromagnet in this material. And based on that, actually, early DFT calculations predicted that this material might realize a 2D Ising ferromagnet with very high strain tunability. Now, this material was discovered in 2019, almost simultaneously in 3 different papers. And it has a Curie temperature of around 50 Kelvin. And for example, here in the magnetization, you can nicely see it's a ferromagnet with certainly some anisotropy. Now, this is the specific heat data of this compound. So basically, or the published specific heat data of this compound, you see 2 anomalies. This one here is the one associated to the ferromagnetic transition. And the upper one here is actually a structural transition, which occurs here in this compound at 80 Kelvin. And there was some debate about what the 2 types of structures here are, but I think there is now, to some extent, some consensus that the crystal structure changes from trigonal to monoclinic as we go through this transition. So in other words, the ferromagnetic transition here in this compound actually occurs in the monoclinic phase and not in the trigonal phase. Yeah. Yes, that's a very good question. I think stacking is not. There are stacking faults also in this material, but I think for those type of materials, all the papers consistently report this structural transition to occur in all crystals studied, and we can discuss that once I show our results because they also relate to that. Okay, so what we were initially interested, or what we then were interested in, is using now hydrostatic pressure because of the predicted high strain tunability to see how much we can tune the magnetism in this compound, but then also to study how does the magnetic transition and the structural transition actually interplay. So how important is the structural transition for establishing the ferromagnetic state? Now, obviously, in this case, it's a van der Waals material, so if we apply hydrostatic pressure, we expect a very anisotropic modification of the coupling constants. But nonetheless, it will tell us something about the tunability of the magnetism. And so the experiments that we did were specific heat under pressure up to 2 GPa. This is a very dedicated setup that I didn't want to describe here in all detail, but I can refer everyone to that publication for details, or I'm happy to discuss later. And so the first thing we did is we take the sample, put it into our pressure cell, and make a specific heat measurements at basically almost 0 pressure. And so we clearly saw here an anomaly which corresponds to that one, the one of the structural transition. We also saw a very nice anomaly here at 50 Kelvin, which is the reported ferromagnetic transition. But then we also found an additional anomaly here at much lower temperatures. And so at that point, we were questioning ourselves, and we decided to ask our colleague Yuji Furukawa in Ames to do some NMR measurements to figure out if this is indeed another magnetic transition here in this compound. And so I'm just showing just a few of his results. The main result is actually here on the right-hand side, which is the vanadium NMR central line at 4.2 Kelvin. And he identified basically 2 peaks, which both correspond to vanadium central lines. And importantly, those two peaks are present below a temperature of 36 Kelvin, which is exactly that temperature. But above that, he only observed 1 peak. So basically, with this microscopic insight, we were able to state, okay, we indeed do have here a previously undiscovered transition between 2 magnetic phases at low temperatures. Now it becomes even clearer actually if we now look at finite pressures. So for example, here I show the 0.04 GPa data that I just showed, and then also a data set at only like 0.35 GPa, very small pressures. But now you see that, well, the structural transition did get a bit suppressed. The first ferromagnetic transition actually more or less stays in place. But the second feature here becomes very sharp and very large and very clearly visible. And also moves rapidly up in temperature. Then if we cross to a slightly higher pressure, then we all of a sudden see only 1 anomaly corresponding to a magnetic transition, which again shifts much higher, as you then can see here in the phase diagram, while the structural transition continues to go down. And last but not least, if you go to even higher pressures, in this case above 1.25 GPa, we only see 1 transition left. So, so what is remarkable about this phase diagram is, first of all, the fact that there is a ferromagnetic transition, namely the lower one, which we can significantly tune by still very moderate pressures of around 2 GPa. So, I mean, here we have within 2 GPa an increase of 35 Kelvin up to basically 70 Kelvin. And if you compare that to other van der Waals systems, like for example, chromium triiodide, which has a pressure derivative of around 5 Kelvin per GPa, this is definitely much higher. So this already implies that in this compound, we have a very strong coupling of the magnetic and elastic degrees of freedom. Now, in later works, actually motivated by our work, DFT calculations, it was suggested that this enhancement is mostly because of a closing of the van der Waals gap at comparably low pressure, so mostly because of increase of interlayer interactions. But this might bring up the interesting possibility to actually check experimentally if a Mott transition in this compound is experimentally accessible. And then again, it would be a Mott transition where we know that there is a strong coupling between the charge/spin degrees of freedom and the crystal lattice. And second of all, what was also then sort of triggered by our work is already in our paper, we mentioned that here, the shape of the phase transition here of the lower one is so sharp that it really looks like a first order phase transition that occurs here at low temperatures. And first order phase transitions are often accompanied by structural changes. So we already pointed out the possibility that here indeed there is another structural transition which accompanies that change between the two ferromagnetic structures. And to some extent, this was also corroborated by the fact that there are 2 vanadium lines in the NMR at low temperatures, while there's only 1 at higher temperatures. So basically then as a result of our work, just I think 2 months later or so, the crystal structure was refined at ambient pressure as we cool down the temperature. And indeed, in this paper here, they were able to confirm our hypothesis that there is another structural change here from monoclinic to triclinic in this compound. And then again, subsequent work pointed out that these distortions are really important for describing the magnetocrystalline anisotropy, as well as spin orbital excitations correctly. So basically, the entire magnetic properties here of this compound can only be described accurately if we take this coupling to structural degrees of freedom into account. Okay, so let me just quickly summarize again what we found here in this compound is, well, first of all, we identified a highly tunable van der Waals ferromagnet in which we were able to double the ferromagnetic transition temperatures with moderate pressures of around 2 GPa. Again, the phase diagram already suggests that magnetoelastic coupling is very important. And this might be a compound which has a very interesting interplay of magnetic orbital and lattice degrees of freedom close to a Mott transition. Okay. Now for the second part of my talk, I want to go back to sort of, I want to switch gears a little bit because now I will discuss results under uniaxial pressure, namely of the elastocaloric effect of a triangular lattice magnet. And so this very nicely connects to what Michael Lang presented in the previous talk. So he, I guess, introduced very nicely these thermal expansion anomalies that are observed in the organic charge transfer salts, and also made the connection that those anomalies are related to basically the physics of the correlated pi electron system on the triangular lattice. He also pointed out that explained that the thermal expansion, or what the thermal expansion measures, is the change of entropy with uniaxial pressure applied along the same direction as you measure the thermal expansion coefficient. So basically, if we measure those thermal expansion anomalies, they give us the initial slope of the entropy if we would apply uniaxial pressure along this axis. But now, of course, what would be interesting is actually to extend those measurements to finite strain and see how nonlinear effects evolve. So basically, measure those type of quantities as a function of finite strain on triangular lattice materials. And now this brings me to an introduction of the elastocaloric effect. I know Jörg introduced that this morning as well, but I will try to give the experimentalist perspective on the elastocaloric effect. So again, if you apply strain and you do that adiabatically, this must result in a change of temperature. And this quantity then, so basically the change of temperature divided by the change of strain, this is what we call the elastocaloric effect. And from thermodynamic point of view, this is related to more or less the temperature divided by the specific heat times the change of entropy with strain. And this to some extent is reminiscent of what might be more familiar to people, namely the magnetocaloric effect, where you use magnetic field to induce temperature changes. And this is then in this case related to the entropy derivative, the derivative of the entropy with respect to magnetic field. Both of these quantities are related to generalized Grüneisen parameters. So here in this case, the strain Grüneisen parameter, and here the magnetic field Grüneisen parameter. And so now obviously if we can measure the elastocaloric effect, then we get a measure of the entropy as a function of strain. And in principle also we are all well aware that the Grüneisen parameter is a very important tool to quantify quantum criticality. Now to do that experimentally, this was actually something which was pioneered by Matthias Igeda in Ian Fisher's group in 2019. So he came up with the idea to use AC strain to then basically measure an AC temperature modulation that you induce by this AC strain. And since it's an AC technique, you can do that very sensitively. Now, you need a device that allows you to apply an AC strain. And for that, we typically use piezo-driven uniaxial pressure cells. Those type of pressure cells were invented and basically made to perfection by Clifford Hicks and Dresden, but are now even commercially available through the company Razorbill. So, and yeah, so what they do is basically, so you mount your sample here, you have a displacement sensor here at the bottom, and then underneath you have piezoelectric stacks. And with these piezoelectric stacks, you apply a voltage, and therefore you get strain. Now you can apply a DC voltage, this gives you then a DC strain, but you can also apply an AC voltage, and this gives you exactly the AC strain that is then needed to measure the elastocaloric effect. And so this is how a typical sample looks like that we mount on here. And then what we do in order to pick up this temperature oscillation to determine the elastocaloric effect is that we attach a thermocouple here into the central neck of the sample where we have the maximum strain. Okay, and again, Jörg showed some of the data this morning, but this is a very new technique which so far has been applied to iron-based superconductors as well as strontium ruthenate. And again, the idea is you use an AC strain to probe the material, but then tune it on top with a DC strain in those devices. And in this way, you can map out basically the entropy landscape as a function of uniaxial pressure for correlated electron systems. And now, if you think about frustration and entropy being an important quantity for frustrated magnets, it's only natural to apply this to also frustrated Mott insulators. So in order to show that we can actually do those measurements, we were choosing our proof of principle example, which is in this case the material called calcium chromate, so calcium 10 chromium 7 O28. I will introduce that material in a second, but I do want to point out that this is a material which grows in very nice large single crystals, which makes our experiments initially much easier because we do need large freestanding materials to do those type of experiments. So now the structure looks a bit complicated, but actually the important unit is this one, which is showed here on enlarged scales. So the proposed frustration mechanism of this compound is as follows. So you have this bilayer system where you have a triangle on the top and a triangle on the bottom. The top triangle is coupled via ferromagnetic interactions, while the lower one is coupled through antiferromagnetic interactions. And then those triangles are coupled through a ferromagnetic transition, ferromagnetic interaction, which then basically frustrates those two subsystems. And yeah, so specific heat measurements were done down to lowest temperatures as well as Newton. So Newton showed diffuse excitations. Specific heat here shows only very broad features, but no kink-like anomaly or phase transition. And also there was a report of 10% R-log to residual low temperature entropy. Okay, so basically what our idea then was can we learn more about this frustration mechanism of this compound through elastocaloric measurements? And what we decided, so the important thing to choose is the strain direction. So we decided for our proof of principle experiments that we would apply strain along the out of plane direction motivated in order to change that coupling here. And so let me start to show some of the data. So this is basically data at 0 DC strain. So here we only use the AC strain to actually probe the elastocaloric effect close to 0 strain. And what we see here is this maximum and here a kink. So basically those very characteristic extrema that are observed in frustrated systems, like Michael Lang showed for the organics, but also this is known for various other materials. Now the fact that our sign here already tells us something, I mean, the sign is positive. So this implies that the entropy at a given temperature is increased by compression if you just look onto this definition here. And just as a sort of two little side remarks, the first one is, obviously, if you just look on the size of the signal, we can compare that. I mean, we can calculate the expected size of that signal based on the reported specific heat and thermal expansion, because the SD epsilon is directly proportional to the thermal expansion. And this is consistent. So the size of elastocaloric effect that we observe here is consistent with typical alpha values for inorganic compounds. And actually last week I heard that Michael Lang has thermal expansion data, and then I can even do that more quantitatively. The second side remark I wanted to do is just give you an idea about how much entropy quantitatively is shifted if we have such a signal. So this signal implies that with 1% strain, we change the entropy by around 1 joule per mole Kelvin. So if you compare that with the residual entropy that was reported at low temperatures, this is of the order of 3 joule per mole Kelvin. Now, this data by itself, as I said, I could measure thermal expansion, I could measure specific heat. Out of 2 separate measurements, I would supposed to get exactly the same data. Now, what is interesting, what happens is if we now start to tune via strain and look at basically nonlinear effects. And this is the data, so lots of things happening. Most remarkable for me is the fact that this broad maximum here starts to disappear and actually changes sign here. And the sign change is a very remarkable point, because as Jörg pointed out this morning, a sign change actually implies that there is a maximum in entropy at this temperature here. On top of that, we do see that this, previously rather subtle kink changes into a fairly pronounced peak here. So what this tells us is very clearly that we have multiple energy scales here in the system that respond differently to uniaxial pressure, giving rise to a very nonlinear change of the Kuhn-Eisen parameter. A very nonlinear change of entropy, sorry. Okay. And so now what we can do is what Andre and Jörg discussed earlier this morning. We can reconstruct the entropy. This is shown here. It does look fairly featureless, but again, this might be not too surprising because these are actually not sharp features. These are just broad signatures of energy scales. So it does look fairly featureless, but we can use that data to reconstruct the specific heat. And so now here, what I'm showing here on the right-hand side is basically reconstructed specific heat as a function of uniaxial pressure. And you can already see that there is a very non-monotonic behavior of the maximum here, and potentially also, or very likely, another shoulder occurring here at low temperatures. Now, in order to put that into context, it is interesting to have a look on theoretical calculations of the thermodynamics of triangular-lattice magnets. And here I'm referring to work by Burkhard Schmidt and Peter Thalmeier, who basically parameterized the triangular lattice in terms of an effective coupling JC, as well as an anisotropy parameter phi. And then basically, so this plot here is a plot of the frustration strength as a function of this angle phi, with the dashed lines being the classical phase boundaries. And obviously then what you find is that the frustration is usually quite high in the proximity of these classical phase boundaries. But now what is interesting, or what I want to look on, is basically the specific heat. And so this is what they then calculated for this model via finite temperature Langshauss methods. And basically what they find is that depending on where I am in this phase diagram here, so basically depending on phi, the specific heat here, the specific heat maximum changes in position and also changes in sign and shape. And so this is sort of important for how I want to put my results into context. But basically what I'm now plotting here is for the entire phase diagram, the result of the maximum position of the specific heat. So basically these points and these points as a function of phi. And you can see that this position here changes a lot and is low whenever you are close to these phase boundaries. And on top of that, you can also have a look on the size of the specific heat. Again, you see it changes quite drastically as we change this anisotropy parameter. So now coming back again to our observations of the specific heat data, and the question of how do those fit into such type of generalized ideas of how specific heat of triangular lattice magnets should look like. And I guess what is clear is if I'm just plotting the maximum temperature of my specific heat anomaly and the size of the specific heat anomaly itself at this maximum, then you see very non-monotonic variations. So compression is here to the left. So we do see initially a mild decrease, but then a rapid increase, for example, here of the maximum temperature. And those changes are only expected, again, if we are close to those phase boundaries according to the theoretical calculations. So to some extent, even if we don't, to some extent, these results already suggest that this material should in fact be located somewhere here in those phase diagrams. And the fact that we do observe at even lower temperatures an additional kink is also remarkable, because in principle, you only expect 2 maxima, again, if you are in this region here of the phase diagram. So here, for example. So basically, if we take that together, it implies that if we do a quantitative, if we manage to map this data on those minimal models, we will be able to position our material very precisely here, and thereby hopefully aid microscopic understanding of the frustration mechanism of these materials. Again, this is work in progress. This is very recent results, but I guess my main point here that I really do want to make is that it is possible experimentally to also measure the elastocaloric effect on insulating materials. This is something which is not trivial, at least for an experimentalist's audience. And that those elastocaloric effects for frustrated magnets do provide us very interesting information about how characteristic energy scales of frustrated Mott insulators respond to strain beyond sort of the initial slope that is measured in thermal expansion measurements. And in principle, if we would, I mean, not for this material, obviously, we didn't find any clear signature of a phase transition yet, but maybe it would occur at lower temperatures or higher pressures. And this technique obviously will be very sensitive to the detection of strain-induced phase transitions. Now, if you take that back to the organics, obviously, it will be very hard to put those organics into such type of strain devices. But the organics with the triangular lattice and their huge magnetoelastic coupling would be obviously prime candidates to study the elastocaloric effect. And if someone manages to do that, I think that would be quite exciting. Yeah, and so this brings me to the summary. I hope that I could convince you that yeah, that pressure tuning is very interesting to study multiple aspects close to the Mott transition. And yeah, I'm looking forward to your questions.